Alrighty, now we're going to look at momentum. So specifically linear momentum, because there's also angular momentum and, hold on. Come on, pen. There we go. So momentum. As with all things, we're going to start with F equals ma. Okay, so this is a vector. So we're back to doing vectors. So energy was just scalars. Momentum is back to being vectors. Okay, so we know that A is dv dt, right? So F equals m dv dt, and I'm going to put the ddt over on the other side, so I have F dt equals m dv. Okay, so I'm going to do this where I'm going to integrate from some initial to some final t, and then integrate from some initial velocity to some final velocity. I'll go v naught. Okay, now we're going to, for the purposes of this, assume that mass is constant with respect to velocity. Assume mass is constant with respect to velocity. And so this we're just going to leave like this, and I'm going to talk about this in a second. Okay, so then we get m integral v dv, so that's just v evaluated from v to v naught. So we've got integral thingy here equals mass v naught. And so I can rearrange, and I've got m v naught plus this equals m v final. Just say final there. Okay, so what I've just done is, again, just taken F equals ma, and I've related force, time, mass, and velocity. So again, these are all the same equations. You can solve all of this with F equals ma. It's just sometimes it's easier to think of it in terms of this. And so since this comes up enough, we gave it a special name, and we call it momentum. Now we're specifically calling it linear momentum. So it's mass times your velocity in a specific direction. So, and it's a vector. And I think your book calls it P. I think the statics book calls it capital L. So get less excited about what the letter is and more excited about what it's called, because all the books have different letters for what it's called. There's also angular momentum, so something is spinning. Okay, so what we have here is initial linear momentum plus something that I'm going to come back to equals the final linear momentum. Okay, now the thingy that I skipped. Okay, so remember that F comes from F equals ma, and those F, remember, is all external forces acting on an object, right? So if I have all external forces acting on an object, that's what this is. So these are only external forces. If you want to kind of remind yourself these are external only, you can. But this has a special name. This is called the impulse. And it's external force times the time over which the force is applied. Okay, does that make sense? Is applied. Okay, so if we have something going on where, kind of like back to that idea of the box. So if we have a box and there's stuff going on, and this is our whole universe, and there's no external forces. So if there's no external forces, here, I'm going to draw like a line so you know this is kind of like a different part of the conversation. No external forces means that the impulse is zero, right? Because that's what it is, because it's the impulse over time, external forces over time. So that means initial momentum equals final momentum. Okay, and that's in a fully contained universe. Okay, with no external forces. If you do have external forces, like if things are colliding and squishing and making noise and heating up and all that kind of stuff, if there are external forces, then you have this impulse. If you have a fully contained universe, then the impulse is zero because there's no external forces. But I think, again, the reason I'm showing you this is whenever I was in school, we always learned these like separately, and I thought they were separate rules, and they're not. This is a subset, so this is like a special case of momentum, of linear momentum. And the special case is that there's no external forces. Okay, does that kind of make sense? So let's see what your book is actually talking about. It's just saying this is the definition of something, momentum. Okay, so they're calling it P, because why wouldn't you call it P? A lot of times by the time we get to the end of the semester, I'm done learning new letters, so I just call it momentum. Okay, is there an example? No, it's just talking about things move fast. Okay, so impulse and collision. So this is where that integral f dt comes from. Okay, that's the impulse that we were talking about. Okay, so this can be potentially weird. It just kind of depends on how far we're going to get into this. And I'm looking at this just like you. So we're going to see. Yeah, so basically the idea is, you know, if this ball is, say, rolling ball, and then I kick the ball, and now it's rolling faster, then it's because its initial small momentum plus the impulse of my kicking it made it go faster. And you're like, yes, I have in fact kicked balls before. And you're like, yes, I understand. But that's basically what you can do is if I can measure the speed before and the speed after, then I can determine what the impulse of that kick was. If I can accidentally figure out exactly how long my foot was on the soccer ball, then I would be able to know what the force was. And if I assume it's constant with respect to time. But anyway, it's an interesting concept. So they're calling impulse J. I'm going to stop paying attention to letters because their letters are confusing me. So yeah, there we go. This is what I was looking for. This is impulse. And I'm not going to call it J because that doesn't make any sense. Why would you call it J? It's just the impulse. Also, I don't want you memorizing letters. I want you actually understanding what's going on. Force over a period of time is an impulse. Okay, so average force, you know, obviously, if you can't do an integral, you can do an average under the curve times the delta, yeah. Okay, and yep, this is just saying that this is the exact same thing. It doesn't look like it's the exact same thing. This is saying that the impulse is the change in momentum. And for the purposes of my brain and things making sense to my brain, I am not going to write it like that because I, as a student, would get confused about like which one goes where and I get the negative in the wrong place. So I always write it as I start with some momentum, there's some kind of an impulse, and then I end with some other momentum. Okay? And like I said, I get to this part of the semester and I'm not even like learning new letters. So, okay. So let's see. What is the average and maximum force that this could have happened? And looking at this, it seems like it's a really good problem until they start just like making up functions down here. So if you're reading this and you're like, where did they get that? And it's like, they just made it up, really. So I'm sorry, we can't fix it. So I'm not going to work through that problem. Let's see. The benefits of impulse. Okay. A car traveling at 27 meters per second collides with a building. That seems unfortunate. The collision with the building causes the car to come to a stop in approximately 1 second. The driver is protected by stuff. What average force does the driver experience during the collision? Okay. So he starts the mass of the driver. And I guess, I'm going to go with, he weighs 860 newtons. All right, so I guess that means 860 newtons divided by 9.81. So 860, 9.81. Oops, I can't spell. I still can't spell. 9.81. So he has a mass of 87.7 kilograms. All right. So he has an initial momentum, and then he has an impulse, and then he has a final momentum. And since I'm just going to assume everything's going in a straight line, I can get rid of the vectors. So I'm just going to say mv1 going straight plus, now I don't have a function for the force and the time, so it's just going to be some average force times change in time, right? Because it's just area under the curve. So that's my approximate area under the curve, equals mass times velocity 2. So hold on a second. There's 2 different times. Which time do I need? So the car stops in 1 second, but he keeps going and then stops in another 2.5 seconds. So is that 2.5 or 3.5? I think it's just 2.5 because he's still going when the car is not going. I think that's kind of the thing, right? So the car stops. So the car's velocity is 27, but his velocity is still 27 until he hits the seat belt, and then the seat belt stops him 2.5 seconds later. Okay. And I think that's kind of the whole point of airbags and seat belts, is they slow the velocity down. So let's look at that. Okay, so we've got his mass is 87.7 times 2.5 seconds equals some unknown f times, oh, I can't spell. That's not where the 2.5 goes. 27, 2.5. And this equals his mass, but the velocity when the car crashes is 0. So 87 times 27 divided by 2.5 is going to be actually negative 947. Right, because if I do the math, I'll get negative 947. So there's a negative force, you know, not that it's negative, but the force is pushing in on him on the left, in the left direction for the driver. Does that make sense? Okay, now it says without the seatbelt, his collision time would have been approximately 0.2 seconds. So let's talk about why seatbelts are important. Okay, so we're going to basically do the same formula. We're just going to change the time, and I think kind of the point of this is to remind you that, you know, seatbelts matter. Come here. You come over here. Okay, so what did it say? 2.5 seconds? Yeah. Okay, so same thing, except now 87.7 and only 0.2 seconds. I'm 80% sure that's what that said, equals 0. So now we have this, instead of being divided by that, divided by 0.2. So now the force is 11,834. So 11,835 really newtons. So you can see the difference in the force that you experience as a passenger not wearing your seatbelt, because it's all about increasing the amount of time that it takes for you to go through that impact. Like, you're gonna have to change your velocity to 0 pretty quickly, but even changing it from like 1/10 of a second to 2 seconds can be life-saving. And I think that's kind of the point of the problem, which is kind of cool. Like, now you can actually do math to show that, you know, whatever you call it, that seatbelts are important. Okay, so there you go. Impulse momentum. Ball receives the impulse. Impulse is added to the momentum. There you go. It's going to be awesome. And then there's a space example that you can look through. Let's see. And I was scrolling down here to see if there's anything else we needed to mention. Here's the special. It's acting like this is the special thing, but this is literally where the whole thing comes from, where we derived it from. So remember when we said F equals ma, and then later on well, then we said F equals M dV dt. Since M is a constant, we can also put it there. So F equals d mv dt, right? So just F equals d momentum dt. And so in your case, in the book's case, it's using dp dt. So if you scroll down, you're like, wait, how come we didn't have that equation? We did. We just skipped it, sort of, or we walked around it. So it's not that this equation comes from what we just did. All those things that were just listed in the book comes from this equation, so they're looking at it backwards. See, there you go. Now they're starting to show it to you. So there you go. That should be plenty to go till we get into the next section.